Hey calculus students, welcome back. It's been a long time since I've made a video for you guys. As we start our next unit on integration, we're going to go through a few things in this next couple of weeks. So integration. So calculus again was created to solve two major problems. One was slopes, rates of change, finding slopes of tangent lines. And we've done that. We've learned about that. The second problem that it was created to solve was to find the areas under curves, or the area between curves. And so that's what integration does. Integration helps us to find the area under a curve. There are two types of integration that we're going to look at. The first type is, and we're going to do them kind of at the same time, working back and forth, but one's called indefinite integration. And indefinite integration is simply where we integrate a function. And we don't actually find an area. The second type of integration we're going to do is called definite integration. And definite integration is where we will now define some endpoints and be able to find an area from here to here under a curve. And so we'll do both sort of at the same time, but today we're just going to talk a little bit about indefinite ones. And indefinite integration is often also called the antiderivative. And basically all antiderivatives is the reverse process of finding the derivative. So on the board behind me here, you see that if we had y equals x squared, and I asked you to find the derivative, you would say, well, dy dx, the derivative, equals to 2x. And the way you would have done that is you would have taken the exponent, multiplied it out front, and then reduced the exponent by 1. You multiplied and then subtracted. To do integration, we simply want to reverse that procedure. So if the question was, if dy dx equal to 2x, find y, the original function. Well, we have to do exactly the opposite. Over here, we multiplied and then subtracted. We're going to reverse that, and we're going to add 1 to the exponent, and then we're going to divide by that number. So it becomes y equals 2x squared. We've increased the exponent by 1, and then we divide by that number, by the exponent. And that will simplify us and leave us with x squared. So we've reversed the process. Now, what we have to be aware of, especially with indefinite integration, is that if I were to take and put a number here, x squared plus 3, that does not change the derivative, right? The derivative of x squared plus 3 is still 2x. So now when I do the antiderivative of 2x, I still get x squared. I don't get the plus 3. And so what happens is, what we're going to do is we're going to add a c here, because we don't know whether or not there was a c there. And I want you to remember what this plus 3 does. This plus 3 does not change the shape of the parabola, right? The x squared is a parabola. It only changes where it is on the graph, right? This translates it up 3 units, all right? So by getting the antiderivative of x squared plus c, that gets us at what's called a family of functions. A family of functions are functions that all have the exact same shape, but are in different spots on the graph. Okay, and so we have to add a plus c. So whenever we do indefinite integration, we're going to add this c because we just don't know whether there was a constant in the original function or not. When we do definite integration, when we have endpoints, those endpoints will define which family we're in, which function in the family we have, and then we won't be adding c. In fact, what happens is the c will cancel out, and so then we don't need it. And you'll see that as we get into what's called the fundamental theorem of calculus, which we will do in our next lesson. So today I want to simply leave you with that. I'm going to give you an example here that I want you to do. It's the only thing. We're going to do two examples here real quick, and that's all I want us to do today. So question again is, if dy dx equals, and we'll do a simple one, 4x cubed minus 6x plus 12, question is, find y. And so to find y, we're going to, in each of these 3 terms, we're going to add 1 to the exponent and then divide by that number. So I have an exponent of 3 here. I'm going to add 1, which makes it 4, and then I'm going to divide by 4. 6, I'm going to make it 6x squared, and then I'm dividing by the 2, the exponent. Plus 12, now 12 is 12x to the 0. We're going to increase that by 1, which will give me 12x to the 1, divided by 1, which I'm not going to write, and then we're going to add a plus c on the end here, because again, we don't know, right? There could have been, if I put a constant here, the derivative would still be what I have here for dy dx. Now we're just going to simplify this, and then we're all done. Y equals to x to the 4th minus 3x squared plus 12x, and then of course we're going to add c. Again, that can be any number that is a constant, and again you can see that if I take the derivative of y, I will get dy dx. Okay, straightforward, pretty simple. We're going to leave it at that for today. I will not give you a second example. Yeah, just let that mull over, and tomorrow or the next day I'll give you another lesson that will be a little more involved, and it will deal with the fundamental theorem of calculus, which has to do with finding integrals, and I will teach a little bit of fun notation as well. So that's it for today. I know it's short, it's simple, and I hope you have a good day, and we'll see you in a couple days.